Hello everybody, welcome to Physics 2053C. This is the first semester of physics with algebra. My name is Professor Lockwood and I'm going to be working with you this semester. Excuse me. Rather than a traditional sort of lecture video, I've chosen this semester to provide you with guided problem solving videos. So I'm going to walk you through the problem solving steps for the different problems that you'll encounter during each module in the course. For this first module, we're looking at units and vectors as well as 1D motion. So starting out with problem 1 here, we're just doing a unit conversion. And this is something if you've taken a science class previously, you've probably done some form of unit conversion prior. And in this unit conversion, what we are doing is we're going to be converting 90 kilometers per hour into meters per second. So we have 90 kilometers an hour, and we want to go to meters per second. Right, so some different things that we know. Looking at kilometers, we're going to be multiplying this by the number of kilometers in an hour, or sorry, number of meters in a kilometer rather. So we know there's 1,000 meters in a kilometer. So this kilo means 1,000, so 1,000 meters. And we also know that in 1 hour, there are 3,600 seconds. 1,600 seconds. That's because you have 60 minutes in an hour, and then you have 60 seconds in a minute. So 60 times 60 is 3,600. So we have basically one on bottom, one on top here. We can cancel those two out. And that means we're going to be multiplying our 90 kilometers per hour by 1,000 meters over 3,600 seconds, which is going to give us 25 meters per second. So moving to question 1.2, question 2, we're looking at vector components. So to set this up, the idea of a vector plays really well off of the idea of a right triangle. So if you've taken a math class recently, you've dealt with right triangles, you probably did some things with maybe Pythagorean theorem, and maybe you also did some things with sine, cosine, and tangent. So when we're dealing with right triangles, we used sine, cosine, tangent. We also used Pythagorean theorem to find sides of the triangle. And we're going to be doing a similar thing here. So what a vector is it is a value represents both magnitude and direction. So what we have in this problem is a vector with a magnitude of 10, and it points 30 degrees above the x-axis. So what that's going to look like is something like this, where we have a vector with a length of 10, and the angle above the x-axis is going to be 30 degrees. And what we want to treat this vector like is just like a right triangle. And we're going to fill in the other two sides of the triangle. One of those sides is going to be what we call the x component of the vector, or the base. And the other side is going to be the y component of the vector, or the height. All right, so if we were treating this as a right triangle, we know a couple different things. So if we labeled our three sides here, we can label maybe this side r, this side y, this side x. We know r squared equals x squared plus y squared. That's Pythagorean theorem. And then we know the ratio of sides. So we know the sine of the angle of this triangle is going to be equal to the opposite, which is y, over the hypotenuse, which is r. And the cosine of that angle will be equal to the adjacent, which is x, over the hypotenuse, which is r. So if we were to find the value of y or x, which is what it's asking us to find here, we would just rearrange our two sine and cosine equations. So we would say y equals, let me write that a little bit more clearly, and I'll do a different color. And say y equals r sine theta, which would be y equals 10 sine of 30, which is going to be 5. And then x is going to be equal to r cosine theta, or x equals 10 cosine 30 degrees, which is going to be about 8.66 meters. And so with this one, if you're using a graphing or scientific calculator, because we're dealing with angles in degrees, just a good reminder to use degree mode on your calculator, not radian mode. Okay, moving ahead to problem 1.3. For this problem, we are looking at a car moving with a velocity of 15 meters per second for 20 seconds. And we're looking at velocity time graph. So let me sketch up a quick velocity time graph here. On a velocity time graph, we will always have time on the x-axis, and our velocity will be on the y-axis. So a velocity time graph of a car moving with a constant velocity of 15 meters per second for 20 seconds might look something like this. So we have like 5, 10, 15, 20, and 5, 10, 15, 20 along the x-axis, the y-axis. Our graph is going to look something like that. And how we can use a graph to find a displacement is the displacement of an object from a velocity time graph is going to be equal to the area between the graph and the x-axis. So that means if we boxed this in, it's going to be equal to that total area. And so if we just think of this as the area of a rectangle, area equals length times width. In this case, our area is going to be displacement, or the change in position. We use delta x to represent displacement. That's going to be equal to length times width. So here I could say my length is 20, my width is 15. So I would do 20 seconds times 15 meters per second, and that would give me a value of 300 meters, which is my total displacement. Moving on to question 1.4. For 1.4, we are dealing with average velocity. So for this problem, we have a runner who runs 100 meters east, we're going to use vectors to represent this, 100 meters to the east, and then they're going to run 60 meters to the west. I'll do this one in a different color. So in order to find average velocity is going to be equal to the change in position divided by change in time. So our change in position is the distance between the starting and the ending point. Right, so it's just this distance here. Right? If we were to find that distance there, it's going to be equal to 100 meters, so 100 meters east, minus the 60 meters, it went west, which is going to be 40 meters. So we can just plug those two numbers in. Now we have 40 meters and we have 8 seconds. We do 40 over 8, which is going to be, I made a mistake. Our change in time is not 8 seconds. Our change in time is 20 seconds. I just caught that because we have to add the two times together. So our change in time is 20 because I added the total times together. I found the difference between the distances to give me the displacement. So 40 over 20 is 2 meters per second. Okay, moving on to problem 5. In problem 5, we deal with accelerated motion. So a bike accelerates from an initial velocity of 4 meters per second to a final velocity of 12 meters per second. When we get into these problems, it's going to be very good for you to list out all of your values given to you in the problem. We're also given time of 5 seconds. And I use the variables representing those values. So v with this little subscript 0, we would call that the initial velocity, or it gets referred to as v naught. Naught means not having, so it's like not having time, or v at 0 velocity. V without a subscript is the final velocity. And t, of course, is time. So then we can look at our equation. Acceleration, or the definition of acceleration, is the change in velocity over the change in time. So our acceleration, we go from 12 to 4, or 4 to 12. Change in velocity will always be final minus initial, so it'll be 12 minus 4, all over 5 seconds. And so that's going to be 8 over 5, or 1.6 meters per second squared for our acceleration. Okay, and then finally on to problem 6. Problem 6, we are going to start to get into kinematic equations. When we deal with kinematic equations, we want to create a full list of values. Initial and final position, initial and final velocity, the acceleration, and the time. And before we even read the problem, we want to have this list. So as we read the problem, we can pause and fill in the list. So it says a car starts from rest. That's an important one. All right, rest means initial. Sorry about that. Rest means initial velocity is 0. And it accelerates at 2 meters per second squared. Acceleration, 2 meters per second squared. How far does it travel in 6 seconds? 6 seconds is your time. And so those 3 values are given directly by the problem. There are other values that we sometimes can infer from the problem, meaning that they're not directly given, but we can assume some things. Right, the first one, or actually there's only one in this case, but the one thing we can assume is that the initial position is 0. But that allows us to solve this problem. So your first kinematic equation we're going to look at deals with position. So our position is going to be equal to the initial velocity times time plus 1/2 of acceleration times time squared. So if you took calculus-based physics, we would derive this equation, meaning we would show where this equation came from. But for this class, we don't have to worry about that as much. But if you do look in the course information section, there is an equation sheet that is posted with a list of all the equations for this class. And this is one of those equations. It's called a kinematic equation. There's 4 different kinematic equations. So before we go ahead and truly plug numbers in, we want to cancel anything out that is 0 in this equation. And in this case, we have initial velocity of 0, meaning that if we plugged 0 into this term, this entire term would cancel out. And the new term, or the new equation, would look like x equals 1/2 at squared. And x, a, and t are all non-zero, so then we can plug in values. So we have 1/2 of 2 times 6 squared, right? Which is going to be 36 meters. All right, notice when I did this, I did not plug or not add any units onto my numbers as I plugged them in. That's because I've already indicated the value of all of the units, or the units of all the values rather, in my list that I've created. Right? I showed seconds, meters per second, meters, so on. To me, this just makes things much cleaner when you're doing the math, because then you treat it just like truly like a math problem. Right? Up until the point where you get to here, writing out this list, writing the equation, canceling values, and getting to this point, that is where the physics is. Only this last step I would consider to be non-physics. This is math. Right? So when I see you solving any of these problems, going back to all the examples previously, really what I want you to show is what are the values, how are those values related through an equation, and then how do you simplify that equation to get it to the point where you can do math to solve. Right? And if you're doing really what I showed here, 3 steps, you do these first 3 steps, if we call this step 1, step 2, step 3, then you are doing physics, right? Step number 4 here, that would be math, right? And I'm less concerned about your ability to do math. While it's still important, my biggest focus is to see that you understand how to apply physical concepts to the scenarios that we deal with. And that's what we're going to focus on in the upcoming modules and for the rest of the course and any future course that you take. And I look forward to recording a video again for you for module 2.